Thank you.
Yeah, I'm Karishma, and I'm here to. I'm a cloud DevOps engineer, and I recently started exploring scientific machine learning. And I have done a project related to modeling the ocean pollutant dispersal, and I'm part of the team who guided me and who helped me in this research project. So my team is from like Visual AI Labs, who have helped me into understanding and dig deep into the problem statement and how effectively we can model a solution for the research work that we have started on. So our journey over the past year hasn't just been about building a single model, but we have focused more on understanding how we can build the models well. So I'm going to explain how we have used Julia and its scientific machine learning ecosystem to conduct a systematic investigation on how to find a robust and reliable method to when applying physics-informed neural networks to complex fluid dynamic problems. So so I would like to start with the problem that we have picked upon, and which is ocean pollutant dispersal. So I would like to explain the scale of the problem that we have initially looked at and how we could improve the traditional methodologies on how we deal with the pollutant spreading across the oceans. So an estimated like 8 to 11 metric tons of pollutant plastic is being dumped into the oceans every single year, and this has been growing every year. And what we wanted to do is have a systematic use physics informed neural networks to model the underlying dynamics when we deal with a pollutant involving like fluid mechanisms. So what you're seeing here is a picture showing a major surface currents of North Pacific. So these large rotating systems are called ocean gyres. So we can think of it as a slow moving whirlpools that span across thousands of kilometers. And they act like massive conveyor belts collecting the debris from the coastlines, and they slowly pull the debris from towards a calm and like a stable center. And as a result of this accumulation is what we see in the next picture, where I have showed it's like a Great Pacific garbage patch. So it's not just like a solid island of trash that is present, but it's a diffuse of microplastics and all the other debris that gets collected on the ocean. So the largest of these patches is estimated to be over 1.6 million square kilometers. So this brings us to the core scientific challenge. So how can we predict or understand how they drift and grow or break apart over the time? So we need to accurately model the underlying physics for it, and this is a very complex and large scale fluid dynamics problem. And where we hit the wall with traditional methods is like simulating these vast domains at a high resolution for decades of time is often slow and computationally expensive. So that's why we kind of tried to experiment on how we can come up with a method that's both physics aware and also data efficient. So that's where we thought like physics informed neural networks can kind of help in having a better way to integrate this. And we believe that the physics informed neural networks offer a more powerful and physics aware and ultimately more computationally friendly and useful way to model this, understanding the underlying physics of it. So a physics informed neural network is basically it considers the experimental data like a general normal neural network, but it is also forced to obey the physics laws that we and govern the equation and consider that in the laws that we build across the neural network. So why did we use it mostly on as a way is important thing that we have considered physics-informed neural network is that it allows us to embed physics laws. So unlike a standard neural network that might only learn statistical correlations from the data, physics-informed neural network integrates our knowledge into the system. So in this case, we have defined a partial differential equation, and we can govern this equation directly into the training process. So this acts as a powerful regularization when and ensures that the solution are physically consistent. So the model learns the rules of the system and not just the patterns that we provide in the data. So, and also they are mesh free, they don't require a complex or often process of creating a computational grid. So this makes them incredibly useful for handling irregular geometries like a coastal line or without any hassle. So the network learns a continuous solution over the entire domain, and which can be evaluated at any point in space and time. So, and also we understand that physics-informed neural networks are very good with data integration, so they can learn from sparse or noisy data. And this is exactly the challenge where this is exactly what we get from the real-world environmental sensors. So they can effectively fill in the gaps between measurements using the underlying physics as the guide. So I think all of these advantages combined will make a powerful tool for the data assimilation and also solve inverse problems. And I would like to explain about how a physics-informed neural network works and how we designed the architecture, the existing to the existing problem that we have picked up. So basically, it's the iterative process of prediction and correction that combines the learning with physics. So we start with our inputs and constants. So in our case, it's time, t, and spatial coordinates, x and y, and physical parameters. So these are directly fed into the physics-informed neural network. And the network, which in our case is a 9-layer 128 neuron network with a tanh activation function. So it processes these inputs and it makes a prediction of the pollutant concentration at that point. And this prediction is then evaluated by a composite loss function. So we use automatic differentiation to calculate the PDE residual, so which forms the the physics loss. And this is where is the main point where we are checking the network's output against the governing physics equation itself. So we also compare the prediction to our reference data, so which gives us the data loss and heavily weighted initial condition loss. So these three components combined into a total loss, so which we have which we have composited like a total loss with the equation, and this single number tells us how wrong the network currently is. And we used the optimizer Adam which uses this loss to calculate the gradients and update the network parameters. So the entire loop repeats multiple times, where each iteration nudging the network closer to the solution that respects the data as well as the physics, and it overall at the end, until we get the output which becomes a highly trained surrogate model. And so I'll explain the specific equation that we are embedding. So our system is governed by the 2D advection-diffusion equation. So this equation is made models two key processes. So the advection term describes how pollutants are transported or carried out by the bulk motion of the currents, and the diffusion term describes how they spread out from a high concentration to a low concentration region due to maybe random molecular motion. So this is the fundamental equation for transport phenomena, and I'll let's take a closer look at the first key physical process in our equation, which is advection. So at its core, the advection is simply the transport of substance by the bulk motion of the fluid. So here the object which is moving within the fluid, it could be, it's the water's movement is transporting it from one place to other place for the object. So mathematically we represent this term, if you see a product of velocity and delta u. So here it represents the v represents the vector which is a velocity of the ocean current. So it shows how fast or in what direction the flow is and the water is moving, and delta u is the gradient of the pollutant concentration. So it tells us how the concentration changes in space, essentially the slope of our pollutant peak. So when we expand this into our 2D model, we get the expression like, which simply says the like total transport, that is the sum of transport in the both directions x and y. And so the plot gives us a visual of how the concentration field might look like at a specific moment of time. So overall advection is a process that would take this entire peak and move it across the domain following the direction of the current. And the second key process that governs this is diffusion. So it's basically where the substance spreads from a high concentration to a low concentration area driven by like random molecular motion. So mathematically this is captured by the term product of a constant diffusion coefficient and delta square u. So here it is, the diffusion coefficient is what quantifies on how quickly the pollutant spreads. So a higher value of diffusion coefficient would mean like a faster and a more aggressive spreading. And the delta square u is the Laplacian. So we can think of it as a measure of the peakness or the curvature of the concentration. So the sharper the peak of the pollutant, the stronger the diffusion effect will be at that point. So this is simply a expansion of the Laplacian in our 2D coordinates, and we have used specific constants for the velocity and the diffusion coefficient for our experimentation. And yeah, so as we looked at the two core physical processes, so this defines a complete well-posed mathematical problem that we are asking our physics-informed neural network to solve. So you see the full 2D advection-diffusion equation where this is the fundamental law of physics that our solution must satisfy at every single point in space and time within our simulation domain. So, but the PDE alone isn't enough to give us a single unique solution. So we also need to provide it the context. That means describe the specific environment of our simulation. So we do this with boundary conditions and initial condition. So we have set a boundary condition for our study where we used a Dirichlet boundary condition. So which means that we are specifying the value of the pollutant concentration at the edges of the domain. So as you can see, like we have set the concentration to be approximately 0 at all the 4 boundaries. So this setup simulates a localized like pollution event happening in the middle of like much larger body of water. So and also the small epsilon term represents a slight noise or measurement uncertainty that we would expect in the real world sensor reading. And coming to the initial condition, this defines the state of the system at the very beginning of the simulation. So initial condition. So we have defined this with Gaussian function, which is like a sharp localized peak of the pollutant standard and effective way to model this. And so the complete task of for our physics-informed neural network is not just to learn from any function that satisfies the main PDE, but it's to find one specific solution that also respects these exact boundary and initial conditions. So this is like a complete well-posed problem that we have set out to solve. And yeah, so to implement all of this, we have built our framework in Julia. we have used quite a few libraries which has been a massive accelerator for our research. So we used NeuralPDE library to symbolically define our PDE system. And this is an incredible feature for random prototyping and also avoiding the manual or error-prone process of implementing like complex discretization. And we could literally write down the math and the library would construct the loss function. The Lux library has provided the flexibility and explicit parameter handling that we needed to define our neural network architecture. And this was crucial for our systematic investigation. And so also the optimization package gave us like unified interface for driving the training process with different algorithms. We have tried it with different optimizers, ADAM-W, and the second order methods like limited memory, BFGS, to test their performance. And we have effectively also used plots and benchmark tools libraries to analyze our results and also measuring the performance with high precision. So the ability of all of these specialized tools to work together seamlessly is what helped us to effectively understand and experiment different scenarios. And we have utilized the strengths of Julia and the libraries wherever we wanted to in the experimentation process. So with this toolkit, we designed a series of control experiments to find the best possible model. So first we needed ground truth to train against. So we generated our reference data using a traditional finite difference method on a 51 by 51 grid. So the process was fast, and also we then added a small amount of Gaussian noise to this data to simulate this kind of imperfect measurements that we would get from the sensors in like the realistic data. So with the problem defined, we have arrived at the core of our investigation, which is like finding the optimal set of hyperparameters for our physics-informed neural network. So the goal wasn't just to pick some numbers that worked, but to conduct a systematic search of the design space. So we looked at the network depth and we tested with initially 5, 7, 9 hidden layers. So we started with 5 layers as a reasonable baseline and pushed up to the 9 layers to see if a deeper and more complex model could capture the intricate features for the solution. And we focused on 9 layers as we see that it has consistently performed well. And the most importantly was the network, the neurons that we have tried out. So for each depth, we have tested 64, 128, and 256 neurons, and this range was chosen to test the network's expressive capacity. So 64 was a common starting point, and but we suspected that it would be too small, and we chosen 128 as a middle ground. And also we experimented with 256 to see how if a much larger capacity would yield better results, but or it would be too difficult to train. So, and coming to optimizer, our primary choice was Adam, and we used different versions with tried with Adam, then improvising it with BFGS optimizers. So we wanted to make sure that the standard deep learning optimizers was indeed the best choice for our physics-based problem. And we have tried out with different learning rates and the durations. So we understand like the too high the learning rate, it would be very unstable, and also if it is too low, it will take longer to converge. So we tried out different learning rates in this range, and also trained up to 10,000 iterations to ensure that every model was given the cases to learn the solution and reach at a stable minimum in the loss landscape. So this approach is what allowed us to identify the optimal configuration, which I'll show in the results. So after running a few of these experiments, so we have come up to an optimal like configuration. So the 9-layer 64 neuron was fast to train, but it consistently lacked the expressive capacity to capture the full dynamics, and it has resulted a higher error of over 18%. And if we consider like 9-layer 256 neuron architecture, it was very slow to train, and surprisingly the accuracy was worse compared to the first 64 neuron network, which is like around 22%. And I think this is because the loss landscape is much more complex and non-convex, so making it difficult for the optimizer to find a good solution. So we identified that 9-layer 128 neuron architecture provided the best balance of accuracy and computational cost. So our best run was with this architecture using a learning rate of 0.06, achieved a final relative error of just 8.25%. So which is a good result for this kind of a problem. And this, as you can see here, the result of this 64 neuron is the loss history on the right. It struggles to converge and has a lot of noise. And like this, the final prediction on the bottom right is, you can see visible artifacts and noisy background compared to the ground truth. In the 256 neuron network, while its final loss is low, you can see the training was more erratic and large spikes in the loss history. And this is the optimal 128 neuron configuration network, where the loss curve is much more stable and converging smoothly, and the final prediction is clean and visually close to the ground truth from the traditional FDM solver. So this kind of makes us understand that simply having a network bigger isn't answer to the problem or the solution to arrive at a effective and less error configuration. So this is our best configuration that we have experimented, and it has resulted in around 8% of relative error. So apart from accuracy, the other key advantage of physics-informed neural networks is their speeded inference. So the traditional FDM solver can compute a single solution in like for our specific problem, it is 0.26 seconds. Training the physics-informed neural network is slow and it's a one-time cost. Our optimal model, which I showed you earlier, it took about 20 minutes to train. So, but once it is trained, our physics-informed neural network became a surrogate model that can generate a new prediction in just 24 milliseconds. So that's more than 10 times faster than the original solver. So this speed is what enables applications like real-time forecasting or large-scale uncertainty quantification studies where thousands of model runs are required. So this is a plot of our best result. So this slide shows like the direct comparison for the winning configuration. So on the top, you can see how a weighted loss strategy allowed the PIN to perfectly capture the initial condition, which is part of our methodology. And here on the bottom, you can see the final prediction at the end of simulation, which is remarkably close to the ground truth. So this is how like we could achieve a desired result by combining a systematic search with the right modeling techniques. So our work, what we have identified is physics-informed neural network is a highly efficient tool for modeling complex physics systems like ocean pollution. And also we have identified that the performance is critically dependent on finding the right balance in network architecture, and that engineering the loss function is the key to achieving accurate results. And this is just a foundation that we have started up with, and it's just really the beginning. And our next steps are to extend this framework to a 3D to capture vertical mixing, incorporating real world time variant ocean data, like ocean current data from satellites, and even explore using these models for scenarios like using sensor data to trace a pollutant back in time to find its source. So this is what we have in the roadmap to extend and improve these more, like taking it as a baseline. And yeah, you can find the source code for this project in the GitHub repository, and also a detailed write-up of our methodology and the results are published in our paper on the archive. So you can scan the QR code to access them. And you can also, I'm also open to collaborating into anything that's more in any work with respect to physics informed neural networks and scientific machine learning in general, and I would be happy to stay in touch and have ideas and thoughts shared. So you can contact me on LinkedIn if to have more to collaborate more on this. And yeah, I think the future of scientific machine learning is bright, and with tools from Julia ecosystem, it's like really building many new things out of it. And I would thank you for the time, and I would be happy to answer any questions or any feedback or any suggestions that you have on this work. Yeah, thanks a lot.
Great job. Thank you for preparing that. We have time for a question if anyone has one. Let's get you in the back first. We should have time for two, so.
Hi, hello, thank you for a great talk. So I have kind of two related questions, kind of short. How do you decide on the velocities that you chose? And that's, I see that they are constant.
Yeah, they are.
And then you mentioned that you want to have like time varying currents. I assume that you want to have that from satellites, but have you thought about like using also the Navier-Stokes equations, right? Because what I think is like when you have the velocity going to the concentration, right, to the pollutant spot, that probably decrease the velocity, and then you will have to take into account to how the motion of the fluid is affected by. Yeah. I mean, can you comment on all of this?
Yeah, that's right. So currently we started with constant values, and we wanted to add those additional parameters that we want to consider when we deal with like a real ocean currents and other, as you mentioned, like velocity reduces over the time, and those are the parameters that we haven't considered as for this initial baseline. And yeah, we would like to explore, dig deep into that aspect. So initially for this as a baseline, we started with the constants, and like we had like a initial constants and the diffusion coefficient, everything is considered for a small grid. And yeah, we would explore more and like improve this more and consider all the variant velocities and all those in the future. Yeah, thank you.
All right, well, I think it's time for the next speaker, so I'll hand this off to the session chair.